Good day. We are still on our quantum computer workshop, Introduction to qiskit, Psyche Basic. Before we go to the Psyche, we want to talk about the socket basic. And before we start going to the socket basic, I want us to talk about what is a qubit. Many of us will be hearing qubit, and how come we get to qubit? Because we have binary and we have bits, and now we are now talking of qubit. Okay, a qubit is a fundamental unit of information of quantum computer. They look very different from classical bits. We have in physics, we have, or let me say, physics magnetism. We have classical and we have quantum magnetism. So now, the present computer age that we are dealing with classical bit, which is just only 0 and 1. So, but this qubit is the fundamental unit, as a bit is the fundamental unit of classical mechanism. So, there are different computing, there are different computing qubits that are used by different computers, such as there are different types of quantum computing. We have superconducting loops, we have trap, trapped ions, which are ions with laser, and we have silicon quantum dots, and also tropically, we have the tropical qubit and diamond, you can say. The question is now you may be asked or you can be asking yourself is how many bits is in one qubit? How many bits? How many bits is in one qubit? Two bits are qubits can hold more information up to 2 bits using super dense coding. So that's that area. 2 bits are qubits. 2 bits are qubit can hold more information up to 2 bits using super dense coding. So actually you'll be seeing it's like a question which I want us to have more understanding on. So what are the first stage of qubit? What are the first stage of qubit? And if you look at it in a normal perspective of classicals, we have first stage of normal computers that we are all using. 2 bits 2 bits in your computer can be in 4 possible states, which is 00, comma, 01, comma, 10, comma, and 11. Those are the 2 bits that our possible state of classical are. And this limits the computers to processing one input at a time. In a quantum computer, 2 qubits can be also represent the exact way of classical 00, 01, 10, and 11. But in this situation is more far and more faster in quantum. And actually we still see how those states going to be in 001, and likewise we can have it in 3 bits 000, 001, 001, and 100, and we still have 101, and so on. So we can work on it to rearrange this. I'm talking of for the one of quantum representing qubit. Representing qubit, why a bit or a binary digit can have a value either 0 or 1, but a qubit can have a value that is either 0, comma 1, or a qubit superposition of 0 and 1. In classical, we have 0 and 1. Let us just assume, okay, if you study electrical or electronics, you will have a socket. If you on your socket, we have the the 0 is is off and 1 is on. It's just normal switch that we are working with in our appliances or in our home. Just on is one and off is what? Zero. That's how a classical bit or a binary digit is. And in quantum or in qubit, zero comma one can be in the same state at the same time, present time. But in classical, it cannot be in the same state. So that's where superposition comes in. Here you have zero and one at the same time, at the same period. Very fast computer. The state of a single qubit can be described by a two-dimensional column vectors of unit norm that is the magnitude squared of the entire must sum to one. So now we are going to be talking of the what two-dimensional columns of what of vectors units that define the qubit. That define the qubit. Um, this vector is called quantum state vector. This vector is called quantum state vector. Here we are having the sum of x 0 comma 1 and x cos theta over with x, and we have 0. And remember something is being represented by bra and ket. So you'll be seeing bra and ket with this sign, this sign, this sign. No, without x, without x, we remove it. So anything can be inside there, which is the case. Anything can be inside there. So you can have zero, you can have one, and so on. So it's always be in what in bra or ket. So that's the notation, part of the notation of key of quantum or bit. Two-dimensional Coulomb vector of real or complex numbers, with number one represents a possible qubit state either by a qubit, a possible quantum state either by a qubit. So now we have our sorry, we have our alpha and beta in a what in a two-dimensional column vector. This is a vector. We have scalar. Um, if you remember our physics, we have vector, we have scalar. So here we have two-dimensional column. You can have three dimension, you can have four. So we have two-dimensional column of a real or complex number. We know what a real number is and a complex number is, with number one representing the possible quantum state held by a what by a qubit. And in this state represents a qubit state if alpha and beta are complex numbers. Satisfy that alpha raised to power 2 plus beta raised to power 2 is equal to what? Is equal to 1. We all have these we all have this um we all have this basic of mathematics. Here we have our cos theta plus sin theta is equal to what? Is equal to 1. So the same aspect of it is now we have our alpha is raised power 2 plus beta raised power 2 is equal to what? Is equal to 1. Some example of valid quantum state vector representing qubits include 0 when they are in what in column vector 0 and 1 and 1 0 we have 1 raised to power 2 1 raised 1 divided by 1 divided by root 2 and a 1 divided by root 2 comma 1 divided by root 2 we still have minus 1 divided by root 2. Likewise we still have the what the real number imaginary number where we are having what I and the state vector and sorry the quantum state vector 1 or 2 and 0 and 2 a take a specific rule which is from a basic for the vector space that describe a vector space that describe the qubit state. This means that any qubit state can be written as a sum of of their basic vectors. Specifically, the vector x, y can be written as x with a column vector of 1, 0 plus y with a column vector of 0, 1 is called a computational basic. It's called a computational basic of that. And we have so these two quantum states are taken to correspond to the two states of a classical bit, namely 0 and 1. The standard convention is to choose 0 is equal to what? 1, 0, and 1 is equal to what? 0, 1. When you go deep in quantum or vector, when you go deep in vector, hereby you'll be having 0. You have to represent your 0 with this. When you have 1, you have to represent your 1 with this. Is when we are doing some calculation and or trying to prove some areas in class in quantum computing. We do this, we make use of this. But actually is in classical bit. The classical bit is 0, but when it's in vector column is this, and is being useful. Let us just have a little look of building the circuit. The basic workflow using qiskit consists of two stages: build and run. Build allows you to make different quantum circuits that represent the problem you are solving, and run that allows you to run them on different backends. So for us to have our qiskit running, you have to first of all do what? Import. You have import numpy as what? MP. And also we have from qiskit import what? Quantum socket. From qiskit import what? Quantum socket. Okay, let us just write some basic code whereby we have QC is equal to quantum socket. I'm trying to import this. I'm calling it. This is what I'm calling. So because actually we've import numpy as MP, and from qiskit, from our qiskit, import this because we are using it, which is this socket. So we have QC is equal to what? We have Q is equal to quantum socket, and from there we create the number of qubits we want to have, both in classical number of qubits we want to have, and our qubit is in what? 8 cube, and we are going to have 8 output. We have 8 we have 8 cube, and it's going to give us 8 output. And for us to have the output, let's let's run this. You will still remember how to run. Okay, sorry. Why is giving me an error message? Because I've not my called my import or the library I'm importing. So okay, let me run it. Okay, and from there let's come back to our what? QC is equal to quantum socket, and from there I'm rerunning it. Okay, perfect. So the next thing is QC, sorry, QC dot measure. I want to measure. I want to measure all. QC measure. Okay. And from there again, we have our to have the output, we have QC dot draw channel state, flow through true. Channel state is equal to what? True. Okay, let's see the result. So that's all he gave to us. Whereby after what we've import our library from qiskit import quantum socket. We now have QC. QC is a variable name which is holding our what our quantum socket, which we have 8 qubits in it, and these are our 8 qubits to do what to measure all. And now give me the output qc dot what output, which is draw. So this is it. So from there make sure it our qubit does not count from one. It's always counted from what from zero, which is what which is q0, Q1, Q2, qubit 1, qubit 2, qubit 3, qubit 4. Sorry, I need to scroll down. Qubit 5, qubit 6, and qubit 7. So those are the measurements that it disposed out to us. So that's the basic. So we can work around this, trying to do what to change this 5, element 10, and see how it's going to work. Thank you.